Good afternoon.
Good
Good
afternoon.
afternoon.
All right, so how's everyone? Anybody do anything amazing over the weekend?
So we had a robotics competition weekend.
Let's see. Wait, didn't you win?
We won,
All
and we
right.
also we broke
We
the state
broke the
record
Arizona
and
state
made
record.
it, and we did that multiple times. So beat the first record, and then we beat the
our
record we had
again
just
a couple
made,
matches later.
Nice.
and then I think we did it again.
Wow.
So we
that's
beat
pretty
it a lot.
That's awesome. You should spread that out a little bit, Let other people have a little chance. No, just kidding. Good job. That's super cool. So, you think you'll go back to nationals this year?
We hope so. We think we stand a really good chance, but there's a really good out-of-state team coming to our state
Yeah.
that puts it in, that makes the whole thing kind of iffy. If it weren't for them, I would say yes, but they're coming, so we will see.
So maybe you could develop a computer virus or something for that group, right?
Yes, that'd be great.
So, anyway, I don't know. I'm pretty sure I told you this, is that I kind of worked with a group, and they got into the championship round. It was a VEX robot convention competition, and then the robot went haywire in the championship round, and they think it was because of a cell phone in the area. And they had all these signs posted because the equipment that they would issue you, I guess it wasn't as shielded as it is now from cell phones. And so they had all these signs: please don't use your cell phones in the competition or whatever. Anyway, but it turned the signals completely upside down. And so the person that was running the robot, I mean, it was literally inverted everything. So it was just really crazy. So
That is weird. One year we were watching the championship round for the first time I went to Worlds, and the team that we were backing, from our division, ended up losing because they accidentally scored in the other team's goal.
Oh no! Oh, that's crazy. That's crazy. Well, so when they talk about, so my awesome thing over the weekend is I went to my granddaughter's blessing in Utah, and so that was super cool. But and we flew up there, and when they say to put your phone in airplane mode because it could mess up the controls, and most people think, there's no way, that's ridiculous. But I actually, after being at that robotics convention, that competition, I thought, maybe there's a chance. If there's some signal that's not shielded properly, it could mess it up. So anyway, well, that's super cool. So nationals in 2 weeks, right?
No, state is in 2 weeks, but we
State's
qualify for Worlds from our state.
Oh wow, that'd be pretty cool. And then you go to Galactic after that, right?
No, they don't have Galactic. They do have, so they decided to make 2 world competitions,
Right.
and then they take the winners from each and they throw them together in Festival of Champions. So we could get really lucky and go to Festival of Champions, but that's the farthest we can go.
That's pretty cool. I'm just thinking then after that it's like Guardians of the Galaxy, right? So you'd be like, Rocket or something. But anyway, all right. Well, so anybody else do anything amazing? All right. Well, that's good stuff there. So, and we gave time for Joey to get here, so now we can get started, right? So, glad to see you all here today. Okay, so where we left off, we've got the last column on 7.6 plus the problem, I think, at the bottom. No, it's just that last column is actually what we have to do. And then I'm hoping that you wrote down the formulas for 7-7 because we're going to just pretty much jump to the practice problems on that. So if you haven't written down the formulas for 7-7, try to do that before class tomorrow. So anyway, well, let's go to this example for 6E. And let's just get started here. So we were talking about applying the formulas that we had last time for the inverse trig functions and so on. And so, but most of those had the difference of perfect squares. And so most of them we were able to plug in pretty nicely. The rest of this section, this 7-6 really is just algebra. It's just algebra tricks. What do we do if it's not quite in the right format? You know, how to, shoehorn it in there. So like in this one, see, we want the difference of two perfect squares. Well, 4x squared is a perfect square. You can think of that as 2x quantity squared. And even though 3 isn't a perfect square, we can think of it as radical 3 squared. And so here we would let a be radical 3, u be 2x, because 2x times 2x is 4x squared. And then don't forget you need to figure out what the du is. So here the du would be 2 dx. And so now we need, so to do the integral here, we need a 2 up here with the dx. So these are the ones where you multiply by a 2 and then a 1/2 out front to compensate it. And then you write this as radical 3 squared minus 2x quantity squared. And now you can apply, this is, so then bring down the 1/2, and then this is the inverse sign of u over a. So 2x over radical 3, and then plus c. And then you can just leave it like that. Okay? All right, so see if you can do that one at the top of the column there, practice 6E. All right, so I'm going to pick Joey.
Okay, I got sine to the -1 of 3x over the radical 5 plus c.
Okay. All right, so one thing, so I don't want you to think of this as an exponent, okay, because it's not an exponent. So just say inverse sign, okay? Because I don't want you to think of it like x to the -1, where you can write it as 1 over x, because you can't this. But I hate the notation anyway. If I were writing my math book, I would have a different symbol for it anyway. So anyway, okay, but good job. Any questions on that? All right, wonderful. All right, now, so the next little trick is if e to the x is part of the inverse trig problem, usually you want to pick that for your u, okay? So like, how I said, like if you have stuff underneath the radical, that's good, or stuff in parentheses. This is another common thing to pick for your u, all right? So let me just show you how that works. So here, see, you might be tempted to pick this whole thing under the radical to be your u. But just let u be e to the x. And so then what happens is then u squared would be e to the x squared, which is e to the 2x. So this is going to be your u squared minus Wait. Let's back up. Okay, hold up. Okay, remember I said don't forget to write down your du. And then I just forgot to do it. Okay, so if u is e to the x, the du is e to the x dx. Okay, now, but see, here's the problem, is that we don't have an e to the x dx. So what we do is we multiply top and bottom by e to the x. Now, this is a little different than the last example where I multiplied the 2 inside and then the 1/2 outside. See, if you're going to multiply by a function like e to the x, then both things have to be inside. You can't bring one outside the integral. Okay? Now, so then this becomes e to the x dx is your du, and then e to the x is your u, and then you have u squared minus a squared, which is inverse secant. Okay? Now, when you look at this problem initially, you think this is going to be an inverse sine problem, u squared minus a squared. But then when you multiply by the e to the x, then you have the additional u, and so then that's going to be 1 over a inverse secant of the absolute value of u over a. So it's 1 over radical 6 times the inverse secant, the absolute value of e to the x over radical 6. And since both of those things are positive, you can drop the absolute value and just have that be your final answer. All right, so go ahead and try that one. The next one, F. All right, Jordan, when you've got it.
I got 1/3 inverse secant times e to the x divided by 3 plus c.
That's it. Okay? So, this is really picky, all right? But again, I guess I'm in a picky mood here today. So when you said the inverse secant times, you say the inverse secant of, because this, what's in parentheses is what's called the argument. And so you're not multiplying it by the inverse secant, you're taking the inverse secant of what's in parentheses. That make sense? Okay. I want you, listen, when you're up there defending your master's degree to a whole group, I want you to be able to express yourself accurately, okay? So when you're defending your master's thesis, I want you to remember me, okay? So anyway, any questions on that one? Okay. All right, so now the last little algebra trick here is completing the square. All right, so in addition to using the formulas and the tables, you sometimes must remember to complete the square. So again, this is algebra. So let me just kind of, actually, let's look at this one. And so this is practice 7. And so let's just kind of work through this together. So let me just show you how I do completing the square. It's a little bit different than the book, but what I do is the stuff that's in the underneath the radical. Okay. Okay. So what I do is I'll actually reorder it. So I like the squared term first. And then if there's a negative in front, factor out the negative. Now, why am I adding 81/4? Anybody tell me why that is?
Because you have to add c to both sides.
Yeah, so you have to add c to both sides, but where you get that c is you take half the middle term and then square it. So 9 halves squared is 81/4. Now here I just converted it, we converted it to a decimal. So you can make it a fraction or a decimal, it's just fine. But then when you're writing down what is actually being squared, see, it's always x and then half the middle term. So minus 4.5 or 9 halves squared plus 4.5 squared. So we really didn't need to multiply this out, because now when we put it back into the formula, see, it's helpful to know exactly what's being squared. And then once you put it back into the formula, see, now this is going to be an a squared minus u squared, and then the du is just going to be 1 dx. And so then this is going to become inverse sine of u over a plus c. So again, you've got to have it before you can apply this formula. You have to have it as the difference of two squares. Okay. So the blank is to complete the square, you add b divided by 2 squared. All right, so go ahead and try practice 7b. All right, Skylar, when you've got it.
I'm lost.
Okay. All right. So, okay. So to complete the square here, what you do is you kind of move the 5 out of the way, and then you're going to add a number inside here to make this a perfect square. And so the number that you add is half this middle term squared. Now, we don't have to reorder this one because it's plus, okay? But what number will we add in here to make this a perfect square?
4.
4. So then you have to subtract 4 out here. So then this is a perfect square. It's x plus 2 squared plus 1. And so then our u is x plus 2, our a is 1, and then our derivative of u is 1 dx. Okay? Any questions, or are you okay up to that point, Skylar?
I think we got it.
Okay, so see if you can finish it off then. Okay, I've got to step out for a minute. So finish this, and then if you haven't started writing down the formulas for 7-7, go ahead and do that, and I'll be back in like 5 minutes, okay? Okay, sorry about that. Okay, so, all right, so do we have the final answer here on this one?
The inverse tangent, x plus 2 plus c.
Very good. Any questions on that? All right. Okay, so that's it for 7-6. All right, so let's look at 7-7. All right, so this is what's called hyperbolic functions. Now, you might not have ever even heard of hyperbolic functions before today. Have any of you ever heard of hyperbolic functions? I mean, not hyperbolas, but hyperbolic functions. Okay, so, all right, so you remember how we can define the trig functions on a unit circle. You might remember, like, if we did a unit circle where the radius is 1, then we can define all the trig functions as like sine of theta is y over r. And so in this case is y over 1. So, so the sine is just the y value on the unit circle. Okay, so that's kind of how we define, one way to define the regular trig functions on the unit circle. All right, and so then if we want the inverse trig functions, then we say, all right, what's the angle that has like a cosine of 1? And so the answer would be 0 degrees or 0 radians. So the inverse trig functions give us the angle that has that trig value. Okay. Well, so if instead of a unit circle, we use a unit hyperbola, then where, I don't know if you remember graphing a hyperbola where the box is, you go up 1, down 1, left 1, right 1 to make the little box, and then the diagonals of the box to do the hyperbola. And so we take the points on the right, the positive side of the positive branch of the hyperbola. And so we can create new functions based on this positive branch of the hyperbola. That's what we call a unit hyperbola. And those functions, instead of being cosine and sine, are the hyperbolic cosine and the hyperbolic sine. Okay, so that's kind of how we define them. All right, so the first set of formulas that you write down are the 6 basic hyperbolic functions. And so basically what these are is it's a way to write these hyperbolic functions in terms of e to the x. And so that's kind of where you start. All of them you can rewrite as e to the x. E to the x minus e to the negative x over 2, and so on. Now, when you look at the graphs, I'm not going to really worry about you memorizing the graphs or anything like that. But when you look at the graph of a function, one thing that you might ask yourself is it even, odd, or neither based on the graph? And remember, whenever a graph is here, this is symmetric about the origin, or if you turn it upside down, you get the same graph. So that would make it odd. But other than that, you don't really have to put this in your notes per se. We're not going to refer to it that much. If you need it, I'll show you how to put it in your calculator. So cosh, or the hyperbolic cosine, kind of looks like a parabola. And so would this function be even, odd, or neither? The hyperbolic cosine.
Even.
It's even because it's symmetric about the y-axis. Okay. All right, then you have the hyperbolic tangent. So here's the hyperbolic tangent. And then here's the hyperbolic cotangent. So are those even or odd?
Odd.
Those are odd. Because again, if you turn upside down, you get the same graph. Okay. The hyperbolic secant and the hyperbolic cosecant. Now, secant is, you know how secant is the reciprocal of cosine? Well, the hyperbolic secant is the reciprocal of hyperbolic cosine, and hyperbolic cosecant is the reciprocal of hyperbolic sine. So that kind of works out. Okay, so looking at this graph, even, odd, or neither?
Even.
And this one?
Odd.
Odd. Okay. Any questions about any of that? All right, now the identities for the hyperbolic functions. So again, you just copy these from your book, but the one that I want you to, first of all, the one that we use the most is, you know, like how we have cosine squared plus sine squared equals 1. Well, with the hyperbolic functions, there's a minus in here. Okay? So I want to point that out because that's different from the regular functions. The regular functions would have a plus in there. But the hyperbolic trig functions, there's a minus. Okay? Then here, it's like the double angle formulas, the power reducing formulas, and then the Pythagorean identities, the hyperbolic versions of those. Okay, then we have the derivatives. Okay, now the ones that I have like in a box are the ones that don't behave like they should or like you think they would. Okay, so like, because see, the derivative of sine is cosine. But the derivative of hyperbolic sine is hyperbolic cosine. So that works okay. But see, the derivative of cosine is negative sine. But when you're doing the hyperbolic trig functions, there's no negative there. Same thing here. The derivative of secant is secant tangent. But here there's a negative that you wouldn't expect. And so I just want to point those two out because those are most likely where a student would make a mistake writing those down. Okay? Any questions so far? All right, now the integral formulas. Again, the two that I want to point out are the integral of sine is negative cosine, but the integral of hyperbolic sine is just cosine. And so there's no negative. And then on this second to the last one, the integral of secant tangent is just secant. But on this one, there is a negative that you would not expect. And so I just want to point that one out. So we're not memorizing any of these. We're just going to get some practice using them. Okay? So it's really not all that bad. But I just like to have a place to put all my formulas. So that's kind of why I create these sheets in lessons like this. Okay? Okay. So the main thing you got to look out for is if there's an argument other than just x, you got to remember the chain rule when you're taking the derivatives. So like if I have the hyperbolic tangent and I'm taking the derivative, it's just the hyperbolic secant squared. Okay? But if I'm taking the derivative of the hyperbolic tangent of 2x, then I do the hyperbolic secant squared of 2x, and then the chain rule says now I need to multiply by the derivative of the inside part, so times 2, and then you can put that in front. So you got to kind of watch out for that, all right? Let's see. So, let's see here. Well, I guess I don't need that. All right, so let's say I wanted to do the derivative of the hyperbolic tangent of the square root of 1 plus t squared. Now, because I know I'm going to need to do the chain rule, sometimes if the stuff inside the parentheses or the radical is a little complicated, then I might even come to the side and write that out and do that derivative separately so that I don't get bogged down. So like here, I bring the 1/2 in front times 1 plus t squared to 1 lower power. Then using the chain rule, then times the derivative of the inside part, which is 2t. Okay? So now when I apply the formula, oh, and then simplifying here, the 2 and the 1/2 cancel, so I have t on top, and then I can move this to the bottom, the square root of 1 plus t squared at the bottom. And so then I say, okay, so the derivative of hyperbolic tangent is hyperbolic secant squared times du dx. So time using the chain rule. So it's hyperbolic secant squared of the square root of 1 plus t squared times, and then the derivative I simplified was t over 1 plus t squared. Now, can I cancel this with this? Can I cancel this radical with this radical down here? What do you think?
No,
No. And why not, Hannah?
because the radical it's like a part of the secant basically, and so you can't cancel it.
Correct. It's the argument of the secant. It's part of the secant. Okay? And so then, but I mean, you can put that in front, but that's all you could do. Okay? All right, so go ahead and try that practice 6A. Or no, practice 1A, excuse me. All right, so Jordan, when you've got it.
I got sine. Is it, how do you say it? Hyperbolic?
Hyperbolic sine.
Okay, hyperbolic sine of the square root of 1 plus x squared, and then that is times by x divided by the square root of 1 plus x squared.
Okay? So you can put the x in front, because you kind of don't want to have it dangling here at the end, because you might accidentally put it under the radical. So I would put that x in front and then like that. So I think that's what you said.
It is.
Okay? All right, any questions on that one? Okay? All right, so let's do B together. So you were saying, how do you say it? Maybe, I don't know. This is, you can also say, instead of hyperbolic sine, you can say cinch. And kosh rhymes with gosh. And then Tana rhymes with Montana, not Miley Cyrus, but Hannah Montana. Koth rhymes with cloth. Setch rhymes with fetch. And then this last one is kind of weird. Kossage. And it rhymes with sausage. But that's another way, instead of saying hyperbolic sine, you can just say cinch. Okay? All right. Let's go to this one. So now to do the integral of here we want to do the integral of the tana. So but you might have noticed that I didn't give you a formula for the integral of tana. Okay? So we're going to derive it right here. I'm going to show you how to do the integral. So you want to write this one down. Well, it's one of your practice problems here. Okay, so what you do is you think of tan of 5x as sinh 5x over cosh 5x. And then say, let's let u be the denominator, cosh 5x. Then the derivative of this, the derivative of cosh is sinh. So the derivative of cosh 5x is sinh 5x dx times 5. So what we need up here is a 5 to get the du. So if I multiply by a 5, then to compensate for that, I have to multiply by 1/5 out front. And so now this ends up being 1/5, and so 5 sinh 5x dx, that's my du over u. So anytime I have the integral of du over u, that's a natural log. So it's the natural log of the absolute value of u plus c. And so now I replace u with what I substituted for u, cosh 5x plus c. And so here's the new formula. So you want to add this to your paper here. So the integral of tan of h du is the natural log of the absolute value of cosh u plus c. Okay, so the last one, we're running out of time, but the last one on the page, see if you can put it in your calculator. Okay? See if you can figure out how to put it in your calculator, and that's your little homework. Well, you can do some practice problems from your book, but I want you to just see if anybody, if you can't, don't worry about it. I'll show you how to do it. But I'm just curious if we have any calculator wizards out there that think they can do it. Okay? We'll start there tomorrow. Okay? All right, you guys have a great day. Thanks for being here. We'll see you.